Hi. I just want to do a brief introduction to what the visualization team is up to at this point, because there are a lot of exciting things coming in the next year or two. We have just started to consolidate, and Micah is one of our JavaScript wizards on the team who's going to show you some software. There are at least 3 things we've been working on. And the first involves visualization. I would call it exploratory visualization. It's not really exploratory data analysis. It's geared toward the idea that we want to support you in looking at, before you do anything with your modeling, things like the distribution of nulls in your data, or scatter plots or histograms showing distributions of individual features. Now, you probably know some machine learning experts say, what's the point of visualization? It's all being done automatically anyway, and you don't have to worry about distributions. Well, they don't know what they're talking about when they say that. The fact is, it's very critical, and I think you'll see in this illustration, as an example, very critical to know how possible assumptions of models get violated and how you might take measures to deal with that. The problem with this first effort that we are involved in is you got to deal with billions of points or billions of rows. You may need millions of columns in your data. How do you visualize those things? The classic ways of doing it, say binning, where you do rectangular or hexagonal binning in order to do a scatter plot, is not acceptable because it introduces patterns in the visualization that would not otherwise be apparent in the raw data. So we've developed some methods that are related to clustering that actually get around this problem. And so some of the plots that you'll be showing can involve just billions of points, and yet you think you're looking at the actual scatter plot of the data. The second area we're looking into is, I would call streaming visualization. So you've got models that are constantly updating, or perhaps you're doing a scoring that can drift off true or get out of control limits, and you need to see how it's drifting. You may throw an alarm that you've got to refit the model, but in what directions is it getting inappropriate? So that's a big challenge, of course. And the third is what Micah is going to show you, and that involves model diagnostics. Now, the oldest prediction model, or one of the oldest, many of you know, is called ordinary least squares linear regression. Dates back to the early 19th century. You have a variable. Let's just think about a simple plot of y on the vertical axis, and that's what you want to predict, and x, a single x predictor or feature on the horizontal axis, and then you have a bunch of points in here. It's a scatter plot. You see all the points. What we want to do is find a line, straight line, that is positioned in such a way that for any value of x, you can find the expected value of y. That'll lie on that line. And after we have fit this model, which minimizes the sum of the squared residuals from that line, those vertical deviations of all the points from the line itself, we want to look at whether they meet the assumptions of that particular ordinary least squares model. So we do something called the Residuals Plot, which is to take the residual values now on another plot here, those little deviations, plot them against the predicted values, and what we hope to see is a nice even band across all those values. And we can feel, if that's the case, that our regression model is appropriate. Now, with machine learning, we don't always fit that kind of a simple model. We sometimes have things like random forests, gradient-boosted trees, and so on, that involve other kinds of loss functions that are not residuals, squared residuals. Those often are called deviances, where we add over all the rows how much there is a deviation from those expected values in the model. And so that has led us to think about a general way of displaying these deviances versus the predicted values in order to be able to diagnose what's going on. So Mike is going to show you how that can actually be put to use.
Yeah, thanks, Lee. So like Lee says, there's a familiar residuals plot. We have done this new work to extend that to other model types. So I'll briefly set up this project that we use to show the visualization. So there's a competition to predict demand for a large commercial bakery, and this data science competition provides a data set. Here we have 18 million rows. Like Lee says, we have this intelligent aggregation method that enables us to show points that represent all of their neighbors. These points are also real points in the data set, and so there's something gratifying about being able to see and touch points that are representative of some ground truth. So once we've taken this large data set and represented it this way, we can look at patterns in the model error. So I took the raw data, I trained models in H2O. So here we have abbreviations for random forests, gradient boosted models, and a general linear model. And so Lee was saying that if these traditional residual plots and these new plots of deviances that we've developed show a model that has captured all of the meaning in the data, then you should see a random field of points. But in fact, you don't. You see some structure here. And we can make that even more apparent if we pick one of the categorical features of the data and color by that feature. And so not only are there shapes that you see, perhaps this wedge, this long curve, but there are also clusters by certain categorical classes. So in this case, the fifth sales channel, these other sales channels. So here we're plotting the model error against the predicted value for these models we've built. Below, we show more plots. We show the numeric features in the data set, the actual values, plotted against the deviance, or this measure of model error. And you'll notice that some of these patterns persist. We see something unusual here. We see a feature that we've thought is numeric, but perhaps, in fact, is categorical. So we're mixing some traditional exploratory data analysis with analysis of the errors or the outputs of your machine learning model. I think feature engineering is an iterative process, and so tools like this can help you improve over multiple passes, multiple times that you engineer features and train new models. So far we've looked at a GLM. In this tool we've built, you can transition between models. So the old points will become gray and fade away, and you'll see the new distribution. And so with a GBM, you have less model error, smaller deviance, and perhaps different patterns. And then we could also look at a random forest as well and see a wider distribution, but perhaps the same structure we saw if with fewer points. So I'm showing you this naive model, a model where we do little feature engineering. We take the data as it's provided by the competition, and we train some models. But what would it look like if you invested a lot of time, took what you knew about this company's business and the features, and built new features, transformed them, did some data science? So here we have the result. So this is a different analysis, again, starting with the same data set, but with many more features, many more columns that we've constructed to better tease out the meaning in this data set. And so, first of all, you'll notice that these points are much more randomly distributed. I guess we see some structure here, but they're much more spread out. And so it's what you would expect to see based on Lee's description of a traditional residuals plot. I'll also say that the same affordance we saw before of picking a categorical variable and shading by the classes or the values in that variable is available here. And then I can scroll briefly and say there are different features. So we've constructed new features. And so you'll see similar plots, but with those new features here. And you'll see many more plots. So I believe that small multiples is a really powerful technique. If you have many features in your data set, you should inspect them all. We have tools that can make that much easier than it may have been before. And so as we go quickly, you see this one has this more random dispersion. We see some are clustered around certain values. So here it's 0. Here it is where we predict 2 and something less than 2. And again, so you see some patterns still emerge. And this may be, yeah, so I'd like to take a closer look here. This may be something that you can explain and a property of a good model, but it's definitely, I think, something you'd like to inspect and like to understand. I was having a conversation yesterday with one of our data scientists at H2O, and he said a tool like this might be useful if you're joining a team and coming to a place where some feature engineering has happened in the past. So people are working on this ongoing problem, have done some clever things, and you'd like to understand, what have they done, and is there a way to be creative? Is there a way to capture some additional meaning that the existing features don't capture currently? So this is a visualization of model error. It's something that'll be in Steam and H2O products soon, something you can use with your own data. And so again, I'll quickly compare. So we have a naive view, and then with some feature engineering. And then like I did before, we can compare within an analysis between different models. And so this is something else I observed. I will say my specialty is this visual experience, building these data visualizations. So some things that I discover when I'm building machine learning models still really excite me. So forgive me if this is obvious to you, but we have a linear model. It's predicting some negative values for demand. And so there are returns in this data set, so that could be plausible, but it's probably not. And so it made me really happy that the random forest didn't really do that. It did that much less. And if we look at the GBM, you see this same threshold at 0. So again, you can use this both to compare analyses and feature engineering efforts, but also to compare models within an analysis. So with that, I'll say thank you. I'll be around. Find me outside. Find me downstairs. I'm happy to talk about visualizing model error and data visualization generally. So yeah, thank you.